Learning outcome 3.5. Given a finite list of Fourier series coefficients, determine the associated time function in terms of sine and/or cosine functions. Working on this learning outcome is the same as learning outcome 3-4, but in reverse. The type of problem we're talking about is where you're given the fundamental frequency, omega naught, you're given a list of Fourier series coefficients, a sub k, and you're asked, what is x of t? We're going to use the synthesis equation to create this, just like we used the synthesis equation to determine our a sub k's when we knew what x of t was. So let's take this example, which is the same one as you saw in learning outcome 3.4. We take our a sub k's, and we use our synthesis equation, and we write all the terms out for our x of t. We have our a sub k's, we have our k value, we have our omega naught value, and we repeat this for every other a sub k. We then group them into pairs with a positive omega and a negative omega. We then want to take those pairs and use Euler's formula to turn them back into a sine function or a cosine function. When we see a plus between the terms, we know it's going to be a cosine. Where we see a minus between the terms, we know it's going to be a sine. We need to make sure that the cosine term is divided by 2, and therefore we need to multiply on the outside by 2. Likewise, for the sine term, we need to make sure it's divided by a 2j, so we need to multiply outside by a 2j. We then simplify this, and then use Euler's formula to turn it back into a trigonometric function. This is the answer we're looking for. Let's take another example. Same numbers as what we had before. We're going to still use the synthesis equation, but now I want you to solve the problem only using cosine functions. We approach it similar to how we did before. We write out our x of t using our synthesis equation. We group our terms. We see we have this minus sign. When we see a minus sign between pairs of terms, we know it's going to turn into a sine function. But the instructions are to convert it only into a cosine function. This minus sign comes from our a sub k, and we can't just get rid of it or that would change the question. Instead, we need to recall that any number can be written in polar form, and then the magnitude will always have a positive sign out front, because magnitudes are always positive. When we write our x of t with our a sub k in polar form, we get the following. Recalling that e to the a plus b is e to the a times e to the b, we have the product of two exponentials, so we can bring those terms together. We're going to factor that minus sign out around the j. We can now group them. We have our pairs. We have a 2 in the denominator. We no longer need to have a 2j in the denominator, and that j is no longer there for use anyway. Everything that was in the argument now comes down as the argument for our cosine. We have now solved this problem as instructed using only cosine functions. Of course, you know that a cosine is just a sine with a phase shift of pi over 2, so this answer should not be at all surprising. Don't just convert your sine into a cosine. Use this method of converting your a sub k's into polar form, because quite often there's another phase we need to add in, and this is much cleaner. One more quick example. We have 3 a sub k, one pair of a sub k, and an a naught. What is x of t? This is to show how to work with the a naught term. It's the same as it was in learning outcome 3-4. We write all the terms out using our synthesis equation, and our a naught now has a k value of 0. It just hangs out as a minus 5. The other terms get paired, rewritten so they have the appropriate denominator, and turned into a trig function.